Okay, so what I'm going to do is I'm going to link a static structural and then also a topology optimization. So I'm setting this link up ahead of time. Let me also I just want to change the material. Okay, so make it out of aluminium alloy. Okay, so aluminium alloy. Alright, so now let's put our loads on. Okay, so here I'm going to insert a cylindrical support, and I'm going to leave it free in the tangential direction. So in here I'm going to insert a fixed support. Okay, and in here I'm going to insert a remote force. Now what I'm going to do is I'm going to use a vector. So let me do the force first, and then for the direction I'm going to choose no, I'm trying to choose an edge. So let me just choose two vertexes, so that's the direction I want the force to go in. So it's effectively the direction that the spring was going in on the real model. Okay, so let me insert a sizing. Maybe we can go smaller than that, so let's use 2 millimeters. Okay, so let me insert equivalent stress and total deformation. Okay, so you can see the stress and the deformation as well. So we can exaggerate that. Okay, so it's a fairly chunky bit of material. So the loads it's going to see in service aren't really going to change much from what we've shown there, because it's basically some sort of rocker being pivoted at one end, so there might be some sort of something other than a fixed support there, but we're just simplifying the model for this demonstration. Okay, so now in the topology optimization, So we essentially have an optimization region. So we've also got an exclusion region. So anywhere where there's loads, it's got exclusions. Okay, so what I'm going to do is I'm going to change those exclusions. So what I'm going to do, I'm going to insert a named selection. So I essentially would like to keep all the areas that I'm now grouping. I'll give it a relevant name called exclude. So now in my optimization region, I've got exclusion defined by named selection. And exclude. So those faces there might be important for mounting. There might be some sort of bearing surface on there. So that surface needs to be integral with whatever part it comes up with. So basically anywhere where it's got the design region, it can remove material from. So we have a response constraint. So here this is saying retain 50% of the mass that's left over after the exclusion regions are taken into account. And the objective is to minimize the compliance. So just in here. So compliance is essentially the inverse of stiffness. So when you're minimizing compliance, you're maximizing stiffness. So the whole goal of this objective of this topology optimization is to maintain the same stiffness with 50% of the mass. So it's going to try and achieve that. So here under the solution, if we click solve, so with the more recent versions of topology optimization, or in fact from version 18, we've got a topology density tracker. So what this does, because this is an iterative process, it starts sort of adding material and then sort of organically growing the structure. So here you can see it sort of adding material. So with each iteration, it's going to hopefully come up with a closed shape, or a shape that's continuous. Okay, so you can see it sort of growing the shape, and then even sometimes where there was material before, it's now removed it. So the idea is once it finishes solving, you don't want sort of little I like to call them clouds that aren't attached to anything. Okay, so that's getting there. Okay, so the important thing is it's maintaining the integrity of those surfaces over there, which I need for mounting. Okay, so we go to the result, we can see we've got a retained threshold. So this is essentially what we're doing here, is we're telling it what we're going to try and manufacture. Okay, so you can see that there's some holes in there. It's sort of got less material over here, and it's sort of cut out a window where we didn't have one before. Okay, so once we've got this, we click on the results and we say transfer to design validation. So what a design validation is you're basically checking on what the topology optimizer has output. So here we need to update. So here first I have to refresh. Okay, now I can go into space claim. Okay, so oops, the one we need. Okay, so I need to activate that. Alright, so we've got the facets. So here if we go to, oops, okay, so if I go to the facets tab, okay, so I'm just doing a check, so it says it's not watertight, so let me try an auto fix. Okay, so now if I check it again, okay, no problems. Alright, so this geometry isn't ready for reanalyzing yet. So what we need to do is we need to do what we call a shrink wrap. Okay, so I'm going to keep the original body, so 10 millimeters is the smallest face that it's going to try and create, so that's too big. So let's go to 2 millimeters. Okay, let me delete that shrink wrap. So I want to preserve features, so that will keep any sharp corners, which is what I want. No. So I'm just trying this is a bit of a trial and error process. You have to sort of try a few different things. So it's very important that you keep the original body so that it's not lost. Okay, so once we have that, alright, so now we can attempt to smooth. So if I triple click, it selects everything. So you can see when it's smoothed, it basically creates a smoother geometry. So you can see I've still got the sharp edge around there, which is what I want. Okay, so you can sort of compare the old to the new. So now I'm going to basically convert this to a solid, which I can which I can basically reuse or reanalyze. Okay, I use slightly different boundary conditions to when I practice this, so it's taking a little bit longer. Okay, let me just suppress that body. So that's the new solid that I've got. All right, so if I go back to the project now, if I refresh that model, okay, so if we look at I'll just show you the geometry. So it was essentially done with slightly different boundary conditions. So this is the geometry that it came up with. And then inside the mechanical interface, so we've used automatic virtual topology. So this basically groups faces together into sort of larger patches. And then in the mesh we've used what's called a patch independent tetrahedron. So then patch independent just means it doesn't respect the small geometry patches, which is we don't want it to do that because some of those are quite small. So then if we look at the equivalent stress compared to the other model, you can see that there's a lot more area that's more highly stressed. Okay, so that's the topology optimization.